Let us continue our discussion with the rate monotonic algorithm. We said that rate monotonic is an online static priority algorithm in which priorities are decided by the periods of the tasks. Shorter the periods of the tasks, higher becomes its priority. And we said that to understand whether a set of tasks will be schedulable using the RM algorithm, we need to perform schedulability analysis and schedulability tests. We saw one such sufficiency based schedulability test based on upper bound, which said that if the summation of utilization of the task set is less than n into 2 to the power 1 by n minus 1, then the task set is assured to be schedulable under RM. In this, n determines n is the number of tasks in the task set. However, this is a sufficiency based test and is a bit pessimistic in the sense that if I have a task set for which this bound is met, it is guaranteed that RM will be able to schedule this task set. However, if this bound is not satisfied, that means the summation of utilization is greater than n into 2 to the power 1 by n minus 1, it is still possible that the task set may be schedulable by RM. So, therefore, it is not a necessary test. So, we do not get both the necessary and sufficient conditions for schedulability of task set using that algorithm, using that bound. However, why do we use that bound? Because the time complexity is just big O of n. We just need to sum the utilizations of the tasks, and then when we have performed the summation of utilizations, we can perform this bound based test. However, if this condition is violated, we still need to understand more carefully whether the task set will be schedulable under RM. Therefore, we need to have a test which provides both a necessary and sufficient condition for schedulability, and this test is based on the response time of the tasks in the system. So, what do we mean by the response time of a task? The response time of a task is the duration between its release time and its finish time. For example, for the task T3 here, if you want to the response time of the first job of T3 is given as follows, can be seen as follows. So, if you see the order of executions, what will happen? T1 has the highest priority because it has the shortest period, its execution time is 1, period 4, T2 has an execution time of 2, period 5, T3 has an execution time of 2, period 10. So, the highest priority is T1 because it has the shortest period. So, it will get a chance to execute first. So, T1 execute first, and after T1 executes, T2 will get a chance to execute because it has the second shortest period length, and only after both T1 and T2 have got a chance to execute their jobs, T3 can get a chance to execute. Now, if we see the execution order under RM, it will be something like this: T1 executes, T2 executes, and then the first part of T3 executes, then then T1 executes again, and after T1 executes, T2 executes at 5, completes its job, and finally, the last part of T3 executes and completes execution at time 8. So, the response time of the first job of T3 is at time 8. Now, what is the mathematical expression that can be used to determine what the response time of a task will be? It is given by this equation here. So, what does this equation tell? It says that the response time of a task is equal to its execution time plus this part. This part is called the interference created by higher priority task. So, interference I for task I, it is the interference created by higher priority tasks. So, where here HPI is the interference created by the set of higher tasks which have higher priority than Ti. We will look at this in a bit more detail. And we say that if a task set is schedulable under RM if and only if for all tasks its response time is less than its period. When all tasks start at their critical instance, that means that all tasks start at the same time. So, tasks in the system can start at different times. However, if all tasks start at the same time, we call that task set has started at the critical instance, and it can be proved that if a task set is schedulable when all tasks start at the critical instant, then for all other instances the tasks will always be schedulable. Okay. So, then this condition for schedulability says that a task set will be schedulable under RM if and only if for all tasks the response time of their first jobs is less than the period of the task when all these tasks start at the critical instance. So, therefore, we now need to understand more deeply what response time is and how such response time can be determined. So, as we said, the response time has two parts. The response time of the ith task is given by the execution time of the task itself plus the interference created by higher priority task. If we look at RM, we will see that during any period of time, let us say the execution time has to complete before its period Pi. So, Ei is its execution time and Pi is its period. So, within this period Pi, it has to execute itself, it has to complete its own execution Ei, and we said that whenever a task with a shorter period comes, I must allow it to execute. So, I must allow the execution of all instances of higher priority or shorter period tasks that come within Pi. Okay. So, in this expression, if we replace, if this is the, we said this is the response time II, this is II, right, this is II. In this II, if we replace this one, Tk belongs to Hp of Ti, if we replace this by Pi and then Pk into Ek, what does this tell us? This part of the expression tells that how many times a higher priority task Tk. So, for this task Tk, Pk is its period and Ek will be its execution time. So, this part tells how many times a higher priority task gets executed within the period of Ti. So, Ti has a period of Pi, Tk is somebody which has a higher priority than Pi and hence has a shorter period. So, within this period of Pi, Tk is going to come multiple times. How many times? At most ceiling of Pi by Pk times. This many times Tk will come for execution within the period Pi, within the time period Pi, and each time it comes, it will take an execution time of Ek. So, Ek is the execution time of Tk. Each time it comes for execution, it will consume an execution time Ek within this period Pi. So, it comes for Pi by Pk ceiling times, and each time it comes, it consumes Ek. So, therefore, this total time is given by Pi by Pk into Ek, and this is the interference that is caused by task Tk. Now, we have to add up the interferences caused by all higher priority tasks. So, therefore, we sum up, we obtain this sum, we sum up for all higher priority tasks Tk, we find that and we add that up. This is the total interference caused by higher priority tasks. So, why did not we use this expression? What is the difference between this expression and this expression? Here this is R I and here this is P I. What is the meaning? So, P I is the, so if we use this bound instead of this bound, this is also a sufficiency based bound. It is a good bound, but it is a sufficiency based bound, meaning that the time, the task T I may not complete exactly at the end of P I. So, it may not complete exactly at P I, it may complete at a time which is earlier than P I. Then the response time, before its response time, we need to calculate the response, we need to calculate the interference caused by the higher priority task before the response time of P I comes. We do not need to calculate the interference caused by higher priority task after the completion of T I itself, after the completion of the first job of P I itself. Hence, this bound here is a sufficiency based bound, it is not the actual necessary bound. The actual necessary bound is given by this one. So, what does this calculate? It says that the response time of the task of the ith task T I is given by the summation of the execution time of T I plus the interference caused by higher priority task within its response time, not within its period, but within its response time, and hence we have this equation. But the problem with this bound is that this R I appears both on the LHS and RHS, which makes it complicated to calculate the value of this response time. Okay. So, let us see how do we calculate the response time. So, we see that the response time is the summation of the computation time plus the interference caused due to higher priority tasks. There is no simple solution as R I appears on both sides. The worst case response time of T I, however, is obtained by the smallest value of R I that satisfies the above equation. So, the catch is to be able to find out the smallest value of R I that satisfies this above equation, and that is the worst case response time. So, how do we calculate the smallest value of R I? Obviously, R I will be something which is within this interval. R I will be greater than 0 and is less than equal to P I. Beyond P I, we do not need to calculate anything, because the period is violated, period or deadline is violated. We are considering here implicit deadline tasks, where deadline of the task is equal to the length, it is equal to its period. Okay. So, so R I is something which is between P I 0 and P I, and we need to find out the smallest value of R I within this interval. How do we calculate the value of R I? Through an iterative mechanism. Let us understand this iterative mechanism now. The iteration starts with R I 0 equals to summation k equals to 1 to I E I. Here R I 0 is the value of the response, estimate of the response time at the 0th iteration. So, R I 1 will be the value of the estimate of the response time at the first iteration. R I 2 will be the estimate of the response time at the second iteration, and so on. Similarly, we will have I 0, which is the estimate of the interference caused at the 0th iteration, which then R I 1 is the estimate of, sorry, I 1 is the estimate of the interference caused at iteration 1. I 2 is the estimate of the interference caused at iteration 2, and so on. So, what do we start with? We start with this. We start with R I 0 equals to summation k equals to 1 to I E I. Okay. One assumption what we have made here is that higher priority tasks have a lower index. So, k equals to 1 to I, k equals to 1 to I minus 1 are the higher priority tasks than T I. So, T 1, T 2, T 3 up to T I minus 1 have a higher priority than T I. We want to find here the response time of T I. And what do we start with? at least all the higher priority tasks will execute at least once, and the task itself has to execute once. So, the response time by which the output will be produced. When will the output will be produced? I have to allow at least one execution. It will be more than that possibly, but at least one execution will always be there of all the higher priority tasks, and the task itself also must execute. So, we will start first with the response time with the response time estimate as summation k equals to 1 to I E I. Then the actual interference between this for in this interval R I 0 will be calculated. Okay. So, then we will calculate I 0, which is the interference caused within the response time I 0, estimated response time R I 0. Now, the actual interference I j I in the interval 0 R j I is calculated using the above equation. Okay. So, for R I 0 we estimate the interference I 0, for R I j we estimate the interference I j. Now, when do we stop? If I j plus E I, the execution time. So, the total actual interference plus the execution time of the task itself, if that becomes equal to the response time, then we say that R j I is the actual worst case response time of T I, that is R I equals to R j I. Otherwise, we go to the next iteration, and the next estimate of the response time becomes R k plus 1 I equals to R I k plus I I. Sorry, not k plus 1, this is j. R using the response time analysis method we just saw, let us calculate the response time of the first job of T3 here. We saw this example of 2 slides back, and we know that the response time R3 of T3 is actually equals to 8. Let us now see how this value 8 is obtained. So, we do this in iterations. So, firstly we have the first estimate of the response time R0, which is equals to the summation k equals to 1 to 3 E I. Why k equals to 1 to 3? Because T3 is the lowest priority task, and which is equals to 5. But I 30 for this becomes what? Equals to 2 plus 2 equals to 4. Why? Because it is the summation, this value of summation, if we see what does it become for I 30, R I is 5. So, 5 by 4 ceiling becomes 2, 2 into 1. So, therefore, the interference caused by T 1 is 2, and R I is 5. So, 5 by P 2, that is again 1, ceiling 5 R I by R 3 by P 2, that becomes 1. So, 1 into 2 equals to 2. So, the interference caused by task T 2 is 2. So, the total interference caused by higher priority tasks is 4. However, what do we have? I 30 plus E 3. So, this is the total is greater than 5. Hence, within this response time 5, I cannot have I cannot accommodate all the interferences of higher priority tasks and also the execution time of T 3. So, it is 4 plus 2, which is equals to 6. Okay. So, 6 is greater than 5. Now, we have the current. So, the next estimate of R 31 becomes what? Equals to I 30 plus E 3, which is equals to 6. But what happens? I 31 becomes what? equals to the interference caused by T1. What is the interference caused by T1? If it is 6, it is again 6 by 4, which is 2. So, 2 into 1 is 2. What is the interference now caused by the task T2? It is 6 by 5, which is 2 into 2, which is 4. So, the total interference caused is 6, and therefore, I31 plus the execution time E3, that becomes greater than 6. So, I31 is 6 plus E3. So, it is 8. So, 8 is greater than 6. Now, so the total this is the total actual interference by higher priority tasks within the estimated response time 6, that is actually 6, and plus I add up the execution time of the task itself, and I get the total time that is necessary. So, the response time cannot be 6, response time has to be something higher than 6. Hence, we move to the next iteration and we get R32. So, R32 equals to I31 plus E3 equals to 6 plus 2 equals to 8. Okay. But I32 equals to 2 plus 4. Why? Because R32 is 8. So, 8 by 4, ceiling of 8 by 4 is 2, 2 into 1 is 2. So, interference caused by T1 is 2, the interference caused by T2 is 8, ceiling of 8 by 5, which is 2 into 2, 2 multiplied by 2, which is 4. So, the total interference caused by task T1 plus and T2 is equals to 6, and we have I32 plus E3 equals to 6 plus 2 equals to 8 equals to R32. Hence, response time of T3 becomes R3 equals to R32 equals to 8. Hence, we obtain the response time of R3 as 8. This we already saw that this is actually so what happens when we ran the schedule on the NAT chart, Gantt chart that we saw. So, hence we saw that the response time of task 3 is 8, and we can see that this response time is less than its period, which is 10. Similarly, in order to conduct the schedulability test, we also need to find out the response time of T2 and T1, and if their response times are also less than their deadlines, that is for all 3 tasks their response times are less than their respective deadlines, we can say that this task set will be feasibly schedulable by the RM algorithm. However, the time required to calculate this schedulability test is pseudo polynomial in nature, and hence it's costly. Okay. With this discussion of response time, we now move to the next algorithm, which is earliest deadline first. Earliest deadline first is an optimal dynamic priority scheduling algorithm. So, we have to see why it is optimal and what do we mean by being dynamic priority. It is an online algorithm, that means the decision for the order of task execution is taken at runtime. It is a job level dynamic priority algorithm, that means the priority of the jobs can vary during execution and is determined during at runtime. And what is the priority? How is the priority determined? A task with a shorter deadline has a higher priority. Now, so therefore, earliest deadline first at any time executes the ready job with the shortest deadline, with the earliest deadline first. So, in this task set we see that the deadline or period of the first task is 4, deadline or period of the second task is 5, deadline or period of the third task is 7. Now, let us see for the jobs how the scheduling is conducted. So, T1 first executes being the highest priority task executes first. Now, after T1 completes at time 1 at this time, the second job of T1 will arrive only at 4, and so the remaining jobs that are active are that of T2 and T3, and T2 gets a chance to execute because it has the next earlier deadline. T3 executes the first part of T3 executes next, and and at this time the second job of T1 arrives. But for the second job of T1, the deadline is going to be 8. For the first job of T1, the deadline is 4. So, this for the second job of T1, the deadline is going to be 8, which is here. But the deadline for the first job of T3 here is 7. So, the first job of T3 has an earlier deadline than the deadline for the second job of T1, and therefore, this job of T3 now has a higher priority than the second job of T1. Now, let us see what happens. So, therefore, although T1 is there, but T1's second job is there, but T3 having the higher priority completes execution at 5. Now, at 5, the second job of T2 arrives. For the second job of T2, the deadline is going to be 10. For the first job of T2, the deadline was 5. So, for the second job of T2, the deadline is going to be 10. Now, between T2 and T1, we see that for the second job of T1, the deadline is 8, and for the second job of T2, the deadline is 10. So, the second job of T1 has a higher priority here, and hence this executes. The second job of T1 executes. Likewise, the other jobs in the tasks are scheduled, and if we see that for RM, this particular task set became unschedulable. We could not schedule, we had a deadline miss at this position. That was because at this position, if we see, T3 became a lower priority task compared to T1 at this point in time. However, for when the second job of T1 arrived, however, in earliest deadline first, we saw that because the first job of T3 had a deadline of 7, while the second job of T1 had a deadline of 8, the first job of T3 remained at a higher priority than the second job of T1, and hence all the deadlines could be successfully satisfied by earliest deadline first, where RM could not satisfy them. So, we say that earliest deadline first is an optimal scheduling algorithm, which means that if there is a schedule for a set of real time tasks, EDF can schedule it. So, if there is any algorithm that can schedule a set of tasks, periodic tasks on a uniprocessor system, then EDF can also schedule that task set. Okay. So, what is the bound? A real time system is said to be schedulable under EDF if and only if the summation of its utilization is less than equals to 1. So, for RM we saw that in the worst case, for a large number of tasks, if summation UI is less than equals to 69%, there can be cases where that task set will become unschedulable. So, if the summation of UI is greater than 69%, then it may become unschedulable. But for EDF, the system remains schedulable if the total summation of utilization is less than 1. So, EDF is able to harness or utilize the complete capacity of the processor, but RM cannot. So, both the RM and the EDF scheduling algorithm was first presented in a seminal paper by Liu and Leyland published in Journal of ACM way back in 1973. However, EDF has its own problems. For example, during transient overload conditions, EDF may fail to meet the deadline of any task. For example, let us say we have this task set and the summation of utilizations is greater than 1, and hence we have an overload situation here. In this overload situation, we see that when T1 having the shortest, the first job of T1 having the shortest deadline is going to be executed first, and it takes 3 time steps to execute and complete set 3. Now, after this T2 will be executed, and we see that T2 has a deadline of 5, but we do not have sufficient time to complete its 3 units of execution requirement, and we have a deadline miss at 5. Similarly, T3 is also going to miss its deadline at 6, not being able to complete its entire execution requirement, and similarly for T4. In comparison, RM has the advantage that only the lower priority tasks will be affected affected by a given task, by any given task Ti. So, the higher priority tasks will always get a higher priority during execution, and due to a higher priority task is never never penalized by due to misbehavior of a lower priority task. So, RM is better in this case. Now, in this situation where everybody misses deadlines, we possibly can have better schedules. For example, we just remove say T2 and T3 from the system and execute only T1 and T2, T1 and T3, then both are able to meet their deadlines, or we can execute T1 and T4. So, comparing between RM and EDF, the most important advantage of RM is that it has a very simple implementation. Being a static priority scheme, suppose if we keep ready queues which are segregated, classified based on priorities. So, I have a queue for priority 1, I have a queue for priority 2, I have a queue for priority 3, and we put the tasks in the queue in the respective queues based on the priority of the tasks. Then it can be easily implemented. The decision of which task to execute when it is just an O1 affair, it can be done in constant time. So, the implementation becomes simple. It can be applied even in systems without explicit support for timing constraints such as periods and deadlines. Why? Because although the priorities are decided based on periods of the tasks, we do not actually require them during execution. We know its static priority, and if we can fix its relative priority, we will just push the task into its relative ready queue, into its respective ready queue, and we do not need to bother about anything else. RM also has this advantage that it provides better predictability for higher priority tasks. We saw that in the case of EDF, deadlines may be missed due to a misbehaving task at the beginning. If a transient overload is caused by a misbehaving task which takes more time to execute than it is stipulated to take, then all tasks suffer due to that. Everybody else afterwards misses its deadline. In case of RM, we saw that higher priority tasks, whenever they arrive, must be given the processor in preference over the lower priority task. So, higher priority tasks never suffer due to a lower priority task. A higher priority task obviously may have to suffer due to further higher priority task than this task, but it never suffers due to a lower priority task. EDF on the other hand has the advantage that it allows full resource utilization. However, we saw that it misbehaves during overload conditions. A much deeper analysis of rate monotonic versus EDF is provided in this paper by Butazzo. Okay. With this implementation, we complete our discussion on uniprocessor scheduling's real time scheduling algorithms for embedded systems.